Okay, Assalamualaikum and good morning, everyone.
Good morning, sir.
Morning, sir.
Morning. Okay, so today we will continue our lecture with a new topic. So last week we have learned about the introduction of automatic control and also how to use Laplace transform to get a transfer function. Now, for today, we will look at the application of transfer function, in which we will try to derive a transfer function from translational mechanical system. Okay, so after completing this lecture, students will be able to create transfer function for translational mechanical system, for system with single degree of freedom, and also system with multiple degree of freedom. Okay, so before we go into uh, learning about how to derive the transfer function, let's look at the motivation behind deriving the transfer function for translational mechanical system. So let's say if you have a restaurant plate dispenser. I'm not sure whether this is available in Malaysia, but basically what happened in this system is that whenever you pick up the top plate, then the spring, the weight on the spring will be reduced, okay? And it causes the spring to rise and allows you to take the next plate until all of the plate has been taken. Then the spring, the platform here will reach the top of the system. So basically, this system is working in a translational, meaning that it can move either up and down or left to right. Uh, it's not having any rotational motion. Okay, so translational motion is something that is moving backward, forward, or upward, downward. So how can we control YT? YT is the position of the platform given any force or weight Ft, which is represented by the plates. So whenever we remove the plate, then the platform will move. So it will move according to a time function. Okay. So basically, we want to find YT when Ft is changes. So we need to derive the equation for YT from the uh, mass spring damper system. Okay, so before we go back into this example later, let's look at on how to derive a single degree of freedom system for translational mechanical system. Okay, so for a single degree of freedom, meaning that it has only one thing that is moving either backward or forward. So in this case, the mass M, the block, can move either forward or backward. So it cannot move upward, okay? Based on the forces applied, it is either uh, forward or backward. So here in this figure, we have spring with spring constant K. We have damper with damper constant FV1. And we have the force, forward force Ft, and maybe friction, okay? Friction between the box and the floor, okay? So it is represented by friction FV2. Okay, and in this example, the box, the motion of the box is represented by xt. So in this case, the direction of x is forward. Okay, along with the direction of the force F. Okay, so before we go into detail, we need to understand what is degree of freedom. So degree of freedom is the number of unconstrained motions. So in this example, the box M can either move forward or backward. So same with the spring damper also can move forward and backward. So if you hold the box, so that it cannot move, then everything will not move. Okay, even though if you apply force Ft, but the box M, you hold the box M so that it cannot move, then everything will not move. Okay, so meaning that there is only one thing that can move, which is the box. Okay, so degree of freedom is the number of movement or number of things that can move. So here, only one thing, or the degree of freedom is one, or single degree of freedom. Okay, so to model this system, we need to follow these modeling steps. So firstly, we need to decide the input and output from the system, and then list the forces acting on the mass M. In this case, we need to draw the free body diagram, and then we need to convert the forces into frequency domain representation. Okay, so we derive the equation in terms of time domain, then we need to convert into frequency domain. Then lastly, we isolate output from input to get the transfer function. Okay, so let's look at these steps, how to model the single degree of freedom system. Okay, so firstly, we need to decide input and output from this figure or from this system. So basically, the input is the force applied. Okay, so we applied force. So the force is the input for the system, and the output is the position of the mass X. So whenever we apply force, the input, then the position M will change. Okay, so the position M of the mass M is the output. Sometimes we can calculate the velocity of the mass M. Okay, so we just find the position and find the derivative x dot. Or we want to calculate the acceleration, we just double differentiate the position. Okay, so after we decide input and output, then we can list the forces on the mass by drawing the free body diagram. Okay, so first we need to convert the figure on the left into free body diagram. Okay, so this is the free body diagram. Okay, so first we need to identify what are the forces acting on the mass. So in this case, um, there are forces from spring, forces from the damper, and forces from the friction. Okay, and these three forces acting such a way that it will try to resist the motion of the box M. So we assume that the position of the box X is directed forward. So the forces from spring, damper, and friction will try to pull the box to its original position. Okay. So let's say the box the box M, the position is forward. So the forces from spring, damper, and friction will be acting backward because it will try to pull the mass back to its original position. Okay, so that's why we have Kx here, Fv1, x dot, Fv2, x dot, all acting backward. Okay, and we have the input force. which is given already by question, acting forward. So the force F is acting forward. Okay, since the box M has a mass, so we need to consider the inertial forces. Okay, so don't forget the inertial forces. And it's represented by this M X double dot. Okay, so we have four forces acting backward, which is in which these forces try to pull the mass back to its original position. And we have the forward forces F, which is applied applied in the direction going forward. Okay. Okay. So how to know Fv1 times x dot and so on? So we have a formula here. So for spring K with constant K, then the force will be F equals K times X. Okay. And then for viscous damper, so damper with constant Fv, then the force will be Fv times the velocity. Okay, so Fv times velocity. So viscous damper also same with frictions. Okay, so friction and damper also have the same formula, which is force equals the constant times velocity for friction and damper. And then for mass M, then the force will be mass times acceleration, ma. Okay, so spring, F equals kx, damper, F equals Fv times v dot, x dot, sorry. And for inertia, for mass, we have F equals ma, or m times x double dot. Okay, kx, Fvx dot, and mx double dot. Okay, so we can convert this into frequency domain using Laplace transform. So we get k times big X. And for damper, we get Fv times S times big X. And for mass, we get ms squared times big X. Okay. Okay, so we only have these three things only. We have spring, damper, frictions, and also the mass. Okay, so this is our free body diagram from previous slide. Okay, so we can convert each of the forces into frequency domain. Okay, so we just convert kx becomes k big X, fv1 x dot becomes fv1 s, mx double dot becomes ms squared, and fv2 x dot becomes fv2s. Okay, then from the frequency domain forces or frequency domain free body diagram, we can write the equation of motion. Okay, so basically you just equate the forces acting backward equals forces acting forward. Okay, so the front part here, the left hand side here are the forces acting backward equals forces acting forward. Okay. And then factorize big X. And after you factorize big X, then you can determine the transfer function. So usually transfer function is output over input. Okay. So X over F. Okay, so let's say if we are interested to find the position of the mass, which is the x. Okay, so we want to find x. So we find the transfer function gs equals x over f. Okay, so we want to find the position x. Okay, so the position x over output f is this transfer function. Sometimes we are interested to find the velocity instead of position. So we want to find x dot. So we want to find s times x. So the transfer function g equals x times s over f. So we rearrange the equation and just multiply with s. And lastly, sometimes we are interested with the acceleration. Okay, so we want to find x times s squared. So the transfer function g equals x s squared over f. So you just multiply the original equation with s squared. Okay, so you get the transfer function. Okay, so any question?
No, sir.
Boleh sikit-sikit faham. Tak pening dah.
Okay, I hope you can understand single degree of freedom, because later on we will see how the multiple degree of freedom works. Okay, and usually in your exam, the question will be multiple degree of freedom. Okay, so let's look at the previous case study about the restaurant plate dispenser. Okay, so this is an example of single degree of freedom because we only have one mass or platform that is moving either upward or downward. So there is no other things that can move independently. Okay, so the platform can move either upward and downward depending on the forces applied. Okay, which is the plate. Okay, so now we can derive this the equation for this system. Okay, so in this example, I skip the steps regarding the drawing free body diagram. So what you can do, you can just draw the block free body diagram. So this is the platform mass, sorry, small m, and then the position is set upward. Okay, y upward. Okay, so first we need to identify what are the forces acting on the mass. So we have damper and spring. So damper and spring will try to resist the motion of M, which is acting upward. So these forces acting downward, okay? Because the mass M moving upward. So we have damper, FV, FV, Y dot. And we have spring, sorry, yes?
Doctor, I have one question. So the
Mm-mm.
FV is the force is going upward or downward? Because FT is and YT going upward, right?
Yes,
So
yes,
if the spring resists, this doesn't mean that it's going downward.
Okay, good question. Okay, so you mean that spring resist kan? Okay, imagine like this. Okay, when the box are moving upward, then spring is stretched kan? But the stretch is actually trying to pull the mass back downward. Okay, So even though the box are moving upward and the spring is stretched, so you can somehow think that the force is actually supposed to be acting upward, but the stretch is actually causing the box to have a force that pull it back downward. Actually there are other force lain, okay, sebenarnya kat sini the reaction force, okay. So the reaction force also equals ky, but we take only the force that are connected to the mass. So for now maybe um, you need to understand just like this lah. Okay, so when the box is uh, moving upward, then all the forces acting on the box will try to pull it back to its original position. Okay, so all the forces will be acting downward. So in this case, okay, later maybe in multiple degree of freedom, we will look at more example, okay, on the direction of the forces. Okay, so we have forces from damper and spring, and don't forget the inertia from the mass. So we have m, y double dot. Okay. And we have the force should be acting downward as well. But I tak tahu kenapa soalan dia bagi positif. Okay. So it should be negative here, but never mind lah. Okay. In the end, it will be just the reverse. The graph will be reverse in the orientation. Okay. Okay. So we get this equation. Then we find the transfer function, and these are the values given for this example. So we just substitute into the transfer function. And then maybe we can further find the time response, or yt. So this is ys. So we want to find yt. So we need to use what we have learned last week, the partial fraction expansion, and also inverse Laplace transform. Okay, so this is the partial fraction expansion. Partial fraction expansion. Okay. And then we get this final equation of ys. Then we perform inverse Laplace transform. So we get yt. Okay, so we are interested to find the relationship of yt with time. So maybe we can plot the graph of yt. So this is plotted using MATLAB. Okay, this is MATLAB. Okay, sepatutnya graph dia naik ke atas lah. Sebab yt in the end, if you look at this system, when we pick all the plates, then the position of the platform should be at the top of the system. But the graph here we get -1, so dia terbalik lah. Okay. So this is the time response. Okay, we call it time response. Time response of the position of platform. Okay, so if you look at this graph, it reaches a steady state value, -1, steady state position, by taking about 6 seconds. Okay, 6 seconds it takes for the system to reach steady state value. So if you think like this, if you take all the plates out from the dispenser, then the spring will take some time to rise up before it stop at the top of the system. So the 6-second times taken is actually slow lah. Okay, so the ideal case that we want is when we take all the plates, then the spring is already up there without taking any time. Okay, maybe zero. So the ideal case, we want the system to have a graph like this. Okay, so after we remove all the plates, then it will straight go to its steady state value. But that system is impossible in real life because it will take some time, okay, to reach a steady state value due to external factors like maybe damping, friction, spring punya rigidity, and so on. Okay, so in our course in automatic control, we want to make the system to behave as what we want. Maybe we want it to be slightly faster, reaching the steady state value. So we add some controller. Okay, so later on we will see how we can do this. Okay, but for now, what you learned so far is to find YT, or the time response. Okay. Okay, so any questions so far?
No, sir.
Jerit. Okay, now we look at a system with multiple degree of freedom. So if you look at this diagram here, we have two masses. We have mass M1 and also mass M2. So how many degree of freedom? Okay, so by looking at the mass, the number of mass, then we know that the system is 2 degree of freedom. But to verify, imagine if you hold M2, if you hold mass M2, you hold it such that it cannot move. Then you apply a force F. Okay, so force F ni kat sini tak bergerak lah, kat tengah ni. Okay, so let's say you apply some force here. Okay, so when you apply force on M1, but M2 is already fixed, so it becomes something like a wall here. Then M1 here can move. Okay, can still move independent of M2. So even though M2 is stopped, but M1 can still move. Okay, move backward and forward. Okay. What happens if we fix M1? So we fix M1, becomes a wall. Okay. So M1 cannot move. Then we apply force on M2. Now M2 can move either forward or backward, independent of M1. So here there are two things that can move independently. Okay, when we fix one thing, the other can move. So meaning that there are 2 degree of freedoms in this system. Okay, so whenever we have a multiple degree of freedom, okay, so this is 2 degree of freedom, DOF. Okay, so to model this system, we follow the steps previously used in single degree of freedom. So first we need to decide the input and output, and then we draw the free body diagram, and then we convert the forces into frequency domain, and then lastly we isolate output from input. Okay, so let's look at this step one by one. Okay, so we decide on the input and output first. Okay, so the input is the force F, which is applied on M2. Okay, so even though force applied on M2, overall it can cause M1 to move as well. Okay, whenever you pull M2, the spring stretch, then M1 can move as well. Okay, but the motion of M1 is not the same with M2. Okay, so meaning that it's independent of M2, independent in terms of the types of motion. Okay. Okay, so the input is applied force, and then we also decide on the output. Okay, so the output can be the mass position. So we have x2, and also we have x1. Okay, So it can be x2 or x1, wherever or which one that you prefer to be chosen as the output. Or you can find the velocity and acceleration. Okay, so in this case, in this example, we want to find x2 in terms of x2. Okay, we are not interested on x1, but x1 can also be one of the output. Okay. Okay, so after we decide on the input and output, ada soalan ke? Okay, after that we draw free body diagram. Okay. So ni tak ada dalam nota. Okay, so after that we draw the free body diagram. So we look at M1 first. Okay, so on M1 we have spring K1, the damper FV1, and spring K2 attached to M1. Okay, so first we need to find all the things or all the elements that are attached on a particular box. Okay, so in this case M1. So we need to identify what are the elements connected on M1. So on M1 we have K1, FV1, and K2. So M1. So the position is we assume forward. So on M1 we have K1, FV1, and K2. So we have three things connected on M1, and meaning that we have three forces that is trying to resist the motion of M1 from going forward. Okay, so all of these element will produce forces acting backward. Okay, so we have spring K1 here, and we have FV1 x1 dot, and we have the spring K2 x1. Okay, so we have three forces acting backward: K1 x1, FV1 x1 dot, and K2 x2, K2 x1 acting backwards. And don't forget the inertia of the mass. So we have M1 x1 double dot. Okay, so we have four forces acting backward. Okay, let's look back at the original diagram. Okay, now we identified all the forces acting on M1. But we have a spring K2 here that is actually connected between two different bodies. Okay, so it is connected with M1 and also connected with body number 2, M2. So it is actually producing two forces lah. Okay? Forces on X1 and forces on M2. Okay, forces on M1 and M2. So just now we assume that K2X1 is acting backward. Okay, so here we also have K2X2. So K2X2 has forces on M2 and also on M1. So just now K2X1 is acting backward. So we have one more forces, which is K2X2, that is applied by the body X2 on M1. And this force is acting forward. Okay, so what you need to remember is that firstly, you need to find all the elements that are connected to the box, to a particular box. So in this case, on M1, we have spring K1, we have FV1, and we have spring K2, all connected to the box M1. And all of these forces will be acting backward, okay, with position x1, okay. So we have k1 x1 backward, we have fv1 x1 dot backward, and we have k2 x1 backward. And don't forget the inertia if you have the mass. And now we need to look at what are the elements that are connected with M1, and at the same time, it is also connected with other bodies. So in this case, K2, spring K2, it is connected with M1 and also connected with M2. So we need to consider the force from spring K2 by position X2. And this force is acting forward, okay? Acting in the same direction of X1. So we have K2, X2 acting forward, not backward, okay? So all the forces acting backwards are the forces about X1, okay? So all X1. So X1, all of the forces are acting backward. All non-X1 is acting forward. Okay, now we look at the body number 2, M2. So on M2, we have one element which is spring K2. And on M2, we have the force, the input force Ft. So we can draw the free body diagram for M2. So on M2, we have one element connected to M2, which is K2, X2. And on M2, we have the input force Ft. And don't forget the inertia from M2. So we have M2, X2, double dot. Sorry. Okay, then we need to look at what are the components on M2 that are also connected with other bodies, other bodies other than M2. So we have spring K2 connected with M2 and also connected with M1. So there is a force from X1 by K2 by spring K2 on the body M2, and this force will be acting forward. So we have K2 X1 here. Okay, so what you need to remember is that all the forces by X2 all acting backward because X2 is moving forward, and non-X2, all the forces that are not X2 such as X1 will be acting forward. So now we have two free body diagram, meaning that we have two different equations. Okay, we have two different equations. So the first equation is from free body diagram 1. And we have the second equation from free body diagram number 2. Okay, so we need to solve this simultaneously. So it is difficult to solve simultaneously using substitution. So that's why you need to arrange them in matrix form. So what you need to do is you need to separate x1 and x2. So all x1 here, and then x2, and x1 here, and all x2. Okay, separate them, x1, x2, x1, x2, and put on the right hand side all the forces, all the input forces. Okay, so here F on the right hand side. Then you need to arrange them in matrix. Okay, so you multiply with x1 over x1, x2. Here x1, x2. So the first element here represent the first equation that is multiplied with x1. So we have m1s squared, we have fv1s, we have k1, and we have k2 here. So you just write all the things in the first element of the matrix. And then the second element is any element on the first equation that is multiplied with x2. Okay, so you have minus k2 here. Okay, so the second row is the second equation. So the second equation, we have negative k2 times x1. So that's the first element here. And the second element is all the things that is multiplied with x2. So we have m2 s squared plus k2. Okay, sorry, this is k2. Okay, so m2 s squared plus k2 as the second element here, and then equals 0f. Okay, to make sure that your matrix is correct, you have to make sure that your final matrix, the big matrix here, is symmetric. Okay, so symmetric means that the diagonal element here, so the element yang sengit ni or diagonal, this element and this element must be the same. Okay, negative k2. Okay, so if these two are the same, then the matrix is symmetric. Okay, so you will find more on symmetric matrix if you take finite element method. Okay, so when you learn finite element method, or if you already taken finite element method, you will find the concept of symmetric matrix. Okay, so if your matrix here, the big matrix here, has element on non-diagonal, the non-diagonal elements are the same. Okay, macam mirror image lah. Okay, then the matrix is symmetric and your matrix is correct lah. It is arranged correctly. Okay, okay, so after you get this matrix, then you can find x1 and x2. Okay, so this is the matrix that we obtained just now. Okay, one ke? Okay, two, sorry. Okay, so after you arrange the matrix just now, then you can find x1 or x2. You can use Cramer's rule. Okay, so I think you already learned Cramer's rule in numerical method. Okay, so if you already take numerical method, so you should be familiar what is Cramer's rule. But I will explain again what is Cramer's rule. So let's say if you want to find x1, so what you need to do is you substitute this matrix 0f into the first column here. So you substitute first column of the big matrix here with 0f. Okay, and then you find the determinant. Okay, so this is actually determinant, not matrix. Okay, determinant. Okay, so determinant matrix is AD tolak BC. Okay, AD minus BC. And then when you find when you substitute the matrix here into the column here, then you divide by the determinant of the original big matrix here. Okay, so determinant of substituting 0f into the first column divided by determinant of the original big matrix. Okay, so for x2, when you want to find x2, then you need to substitute 0f here into the second column. Okay, substitute into second column and then divided by the determinant of the original matrix. Okay, so that's Cramer's rule. So if you want to find x1, just substitute the column here into the first column. If you want to find x2, okay, just not x1. If you want to find x2, substitute into the second column. Find the determinant divided by determinant of the original matrix. Okay, later, maybe next week, we will discuss on the tutorial number 3 on how to find the either x1 or x2 using Cramer's rule. Okay. Okay, any question before we move on to next section? Yep. Sin yang mengangkat tangan. Ya, malu tanya. Okay, I hope you guys mungkin tak dapat lagi, tak faham lagi sekarang, but you can try tutorial given in kalam, okay? Bolehlah try discuss dengan kawan ke apa ke, okay? Nak tanya? Malu lah tu.
Nak tanya saya. Dalam free body diagram yang example tadi tu, macam mana kita nak tahu dia punya direction, backward dengan forward?
Ini?
Ha.
So usually X1 dengan X2 ni dia akan bagi dalam gambar. So like X1 dalam gambar ni dengan X2 dia bagi forward. So all the forces from spring damper will be acting backward, okay? Sebab kita assume X1 moving forward. But in other example, dia tak bagi X1, dia tak bagi X1, dia tak bagi X2. So we need to assume lah. If we assume X1 moving forward, then all the forces acting on X1 will be acting backward, okay? Tak tahu menjawab ke tak.
Jadi kalau yang untuk yang kotak yang kedua tu, dia assume X2 yang ke depan. Jadi dalam kita punya free body diagram, dia punya force tu akan jadi ke belakang lah. Yang untuk X2.
So all the forces that is multiply with X2, macam K to X2, M to X2 double dot, all the forces acting backward. Sebab X2 kita assume moving forward.
Lepas tu sir, yang kat sini ni kan dia ada macam elemen yang ditunjuk dalam gambar tu, ada yang ada anak panah tu 1, 2 dengan spray tu kan. Tapi bila yang selukis dekat dalam gambar tu, dia ada lebih kan, ada macam extra yang ni. Yang X double dot ni dengan yang
inertia. So inertia ni mesti ada kalau box kita ada mass. So kalau ada mass, mesti ada inertia effect, ada inertial effect. Kalau kata box tu tak ada mass, then tak adalah M1 X1 double dot. Okay, yang tu kena ada sebab ada mass. Yang satu lagi yang depan ni sebab dia berkongsi, elemen ni berkongsi antara dua box. So K2, spring K2 melekat pada M1, dia juga melekat pada M2. So dia ada force dari M2 sikit, dia ada force dari M1 sikit. Cara lain tulis dia mungkin yang tak tahulah belajar dinamik macam mana kan. Yang ni dua kita boleh combine kan. Like you can write the force acting backward, but the total force is K2 x1 minus x2. Okay, so you can also write like this, sama juga, but I prefer separate them because it's bagi saya lagi senang nampak berbanding gabungkan saya jadi pening. Mungkin ada student yang rasa gabung lagi senang faham bagi dia, tapi if you gabung, make sure the direction is correct. Okay, so if you don't write the direction backward, let's say if you write the direction let's say forward, tak keluar pula.
Okay, sir.
Okay, so kalau direction dia backward, forward, then tak gerak. My god. Okay, so you need to write k2 times x2 minus x1. Okay, dah jam. Sekejap Hayya, boleh jam. But don't worry, kita akan tengok nanti dalam tutorial. So when you do tutorial later, try to do it, discuss with friends ke. Then we look at how to model system with multiple degree of freedom. Okay, so now let's look at another case study in which in this case study we want to study the car suspension model. So usually in a car suspension model, we have a spring and damper, and usually there are two masses connected together. Okay, so the mass number one is the wheel, and then the mass number two is the car body. But in this example, instead of having input as the force, but now the input is the road altitude or ketinggian jalan, okay, the road surface. So R here is the position or the height of the road instead of the force. So instead of force, kita guna height of the road, okay. And then the output can be the motion of the position of the car body or position of tire, okay. So whenever you have a height of the road as the altitude, then dia punya model dia lain sikit lah, okay, a bit different. So we usually ignore gravitational forces. Okay, kita assume tak ada gravity. Ada gravity tapi dia macam cancel, okay. So if you look at the first free body diagram for M1. Okay, so look at M1. So on M1, the position X is assumed to move upward. Okay, so on M1 we have spring KW, we have spring KS, and also we have shock absorber or damper B. So let's look at KW. So KW will produce force that is acting downward. Okay. Okay, so ada dua free body diagrams. Jawapan ni sama je, okay. So the free body diagram on the left is the one that I said you can write K1 times X1 minus X2. Okay, boleh tulis macam tu. Okay, but my free body diagram guna separate, okay. we write the forces separately. Okay, so on M1, we have position acting upward X, and on the wheel, we have 3 components connected. We have spring KW, spring KS, and also damper B. So first, we have spring KW. So this will be acting downward because we assume X acting upward. So spring KWX, and we have spring KS X. And we have the damper B times X dot. And don't forget the inertia, M1 X double dot. Okay, so if you look at the left-hand side punya block diagram, so we have KWX. So we have KS X but negative because the direction written or drawn in the free body diagram is upward, but my direction downward, so tak ada negative. So we have BX dot here. So same case, the direction drawn is upward, mine is drawn downward, so no negative. And we have the inertia. So dia tak tulis inertia sebab dia guna kat sini Newton's second law. And now we look at the components that are also connected with other bodies. So in this case, we have KS connected with M2. We have B connected with M2. So we have forces, 2 forces acting upward. Okay, so we have KS, Y, and we have B, Y dot. Okay, sorry, same thing here. Okay, now the only thing not drawn in my figure is R, effect of R. Okay, so if you look at the spring KW, it is also connected with the surface, the road surface. Maksudnya they connected with other things lah. Okay. So we need to apply one more force to consider the effect of road surface. So the force will be acting upward because it is connected with other things, okay? So it's KW times R. So R is position. So since R is position, you treat R as a displacement, something similar with X and Y. Tapi dia adalah position of the road surface. So my KWR is acting upward. So the left figure, KWR there acting downward. So it has negative here. So mine KWR don't have negative because the direction is acting upward. So if you write the equation of motions for this free body diagram, you will get the same thing as the equation shown here. Okay, now let's look at the second body. Let's draw the free body diagram of the second body. So M2, we have 2 spring and damper connected to the body. So we assume M2 acting upward, Y. And the spring KS will produce force acting downward, KS, Y. And also damper B, Y dot. And we have inertia. And the spring and damper also connected with M1. So we have KS X acting upward. And we have BX dot. We have BX dot acting upward. So it's the same thing here, but it has negative because the direction drawn is going downwards, okay? So if you write the equation of motion, you will get the same thing as here. Okay, now we can write the equation. Okay, this is the equation from previous slides. Then we can convert into frequency domain using Laplace transform. So this is the R just now. So the R, you convert, you get RS. Okay, so usually you want to find, we are interested to find either X over R or Y over R. Okay, mana-mana lah, okay. X over R or Y over R. So you can write in terms of matrix and use Cramer's rule. Or in this example, dia guna substitution. Okay. So substitution, it looks macam mana ni tiba-tiba dapat. Okay. So I think it's better if you use Cramer's rule. Okay. Because later on there will be more than 2 degree of freedom system, maybe 3 degree of freedom. So using substitution memang susah, okay? Memang difficult lah. So you need to use by matrix or Cramer's rule, which is simpler. Okay, so that's all for today's class. Habis dah. So I hope you can do or can try tutorial number 3. We will discuss tutorial number 3 next Monday. And any question? Ya, video dalam YouTube. Tapi saya tak share link dah. Saya assume link yang sama tu buka lah channel saya. Macam tu.
Subscribe, Doktor.
Subscribe. Don't forget to subscribe to my channel. Increase my subscriber. Increase my view. Bagi saya duit. Okay, so I hope you can understand translational mechanics. Because later when we go into rotational mechanics, konsep dia lebih kurang sama macam translational mechanics. But it's rotational, okay? Dia rotation dia lain sikit lah, tapi konsep dia sama. Okay, we need to look at the forces and then where the direction goes, backward ke, forward ke. Okay, try to understand, try to do the tutorial. Okay, tutorial kan tak apa, buat salah. Later when we discuss, you can correct yourself, okay? And don't forget, we have a quiz that will be released maybe Friday or tomorrow, I'm not sure. So keep checking Kalam. And for project 1, you can already start part 1, okay? So part 1 is about lecture number 1. So it should be, you should be able to do it by now, okay? So part 2 and part 3, you need to wait until chapter 3, lecture 4, 5, tak ingat, okay? Okay, any question before we end our lecture?
No, sir.
Ada apa-apa sir? Boleh.
Okay, tak apa. Later when we do tutorial, I hope you guys will get more understanding on this topic, okay? So that's all for today. Any question, you can ask me in WhatsApp, okay? So that's all. Thank you. Goodbye. Assalamualaikum.
Thank you, sir.
Yes, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.